Welcome to this video on an introduction to calculating capacitance, and specifically focusing here on parallel plate capacitors, and hopefully the process that we'll use to calculate the capacitance will allow you to solve for different kinds of capacitors like spherical or cylindrical capacitors fairly easily. And this is a calculus-based approach, and so if you are looking for the algebra-based approach, you probably want to go and check out the earlier videos. Either way, it's a good idea to check out the earlier videos because in those we defined what capacitance was, right? Which is the ratio to the amount of charge a region or plate can hold relative to the voltage across those two regions or plates. We also found that the capacitance itself does not rely upon Q or V, right? Q and V is the ratio that describes the capacitance. So what we're really saying is that the capacitance is geometrically determined by epsilon naught, A, and D in the case that we talked about so far. So basically, if the ratio of Q to V is a certain value, it's not because of Q or V individually, it's because of the makeup geometrically of the capacitor. And so that's where we're going to go from. We proved this, or we derived this experimentally in the last videos, and the experimental evidence, right, showed us this. But what we're going to do now is look at a more theoretical approach. And the theoretical approach is going to allow us to come up with the value of capacitance for really any configuration as long as we have the tools. And the tools are going to be to find Q and then to find V. Finding Q, we're usually going to use Gauss's law to do that because capacitors are oftentimes symmetrical situations, so that's great for using Gauss's law. And we're going to use our definitions of voltage. So if you missed any of the videos on finding Q, finding V, you probably want to go back and check those out. So let's say I have these two metal plates, and of course we're just looking at a cross section. I'm going to attach them to a potential difference, or a battery in this case. This is going to leave the top plate positive. We'll go ahead and just draw this on, and this is going to be uniform, and we're going to ignore the fringing or the edge effects. We're just going to eliminate those. Okay, so I charged the capacitor, so I can remove the battery now, and it should hold its charge as long as the plates don't touch or the charge leaks out into the atmosphere. And what happens here is the electric field is now established, and the electric field is going to be uniform. I think I said that already, and we're ignoring fringing. So we have this uniform electric field pointing in the negative y direction. And what we're going to do is, our goal is to figure out what is Q, then what is V, and if I take those two expressions and divide them, the quotient should give me the capacitance. So as I usually would do, I'm going to use Gauss's law here, not to figure out what the electric field is, but actually to figure out how much charge I'm enclosing. If I put the Gaussian surface around both of these plates, then I've enclosed no charge, and I have no flux, and therefore I can't figure anything out. But if I only enclose the charge on this one plate, and I'm going to go ahead and do it like this, then I have some enclosed charge, and the charge on the top plate is the same as the charge on the bottom plate, just a different sign. So using my Gaussian surface, which here would be a rectangular prism, if I think about that, I only have a flux through the bottom surface of the rectangular prism. So if I isolate that, you could think of the field lines passing through like this. The sides and the top are not having any field coming through them. There's no flux. And you can see specifically I just enclosed the bottom surface and not the entire plate because I didn't want to include the flux at the top. Now what I'm going to do here is I'm going to say that due to Gauss's law, we know that the integral E dot dA is equal to the flux, which is also equal to the amount of Q enclosed over epsilon naught. So the amount of Q enclosed is equal to epsilon naught times integral E dot dA. Now, in this case here, where the electric field along the surface is constant, right, we can pull out the E value, and then we can integrate across the surface. And the surface here, I'm just going to call that A. I'm not going to do length times width. I'll just call it A in general. So I'm going to do Q enclosed is equal to epsilon naught E times A. So I have an expression now for Q on the plate, and so I will eventually take this expression and substitute it in. But I first need to take a look at finding the voltage. And finding the voltage is going to take us just a little bit more explanation in order to do that. So let's go ahead and look at that. So we know that our expression from the previous videos that we came up with was that delta V, V final minus V initial, is equal to the negative integral of E dot ds, and this dot product. Now we're going to do something very specific. Going from the initial to the final spot, the path that we take, we're always going to start at the negative plate. And this is just strategic. We're going to start at the negative plate, and we're going to make our path go to the positive plate. So from negative to positive. So my initial starting point is negative. My final ending point is the positive plate. Now doing that allows ds and E to be 180 degrees relative to one another. And so the cosine of that is going to be negative 1. And when I have a negative 1 for my cosine, then this whole expression becomes negative, and the great thing is then this becomes positive. Now my initial is also my zero potential, and this would be my high potential. So essentially what I can write then is just that V is equal to integral E ds from negative to positive. Now if I went from positive to negative, then of course that's a positive cosine value, and then the negative would stay. So in order to eliminate the negative here, that's why I'm going from negative to a positive. So that's my reasoning for doing that. Now I want to know what the potential is across the plates, and let's just say that the separation distance generically is d. And so what we're going to say is E's constant, and I'm going to integrate from negative to positive over that path d with all the little ds's, and when I sum them all together, I just get the total d. So V is equal to E times d if I go from negative to positive. So I have an expression for the charge on the top plate. I have an expression for the voltage across the plates. And now what I'm going to do is take those and put them together in the capacitance equation, which is Q over V, the definition. So Q enclosed here is epsilon E times A, and V is E times D. And we can see the E's will factor out, and the capacitance is equal to epsilon naught times A over D. And so we see here that the theoretical approach yielded the same experimental approach expression. And so we can confirm that this is in fact what determines the capacitance. Now, what we will look at in subsequent videos is how do we do this same process, the same procedure for a spherical and for a cylindrical capacitor.